Hello, this video is to go over how to draw and find forces when you have a wire carrying current through a magnetic field. This is the second set of notes for 5.4. This is magnetism. So this should add on to what we did already with charges moving through a magnetic field with our QVB force, where we used right-hand rule number 1 to talk about the force on a charge moving through a magnetic field. Today we're going to look at when I have a wire actually carrying current through the magnetic field. Since that's a whole bunch of charges moving through the field, we'll talk about how those wires get pushed and pulled. There's a video from MIT with a demonstration of this with two wires kind of pushing and pulling on each other that you can check out as an intro here, and then we'll look at it again once we get to it, of how these wires push and pull on each other with magnetic effects. All right, the first thing you want to make sure you have is how we draw magnetic fields for wires that are carrying current. We said this in a previous set of notes, but we'll get into it here. When a wire carries current, so when charge flows through the wire, I have what's called a circular magnetic field gets created. So we'll look at how to draw these circular fields. The one thing you want to know about the field, you don't need to know the equation. The IB won't ask you for equations to talk about the strength. You just want to know that it's inversely proportional to distance from the wire. Meaning, like most of our fields, the further away you are, the weaker the field is. And inversely proportional means if I double the distance, the field is 2 times weaker. So to draw this circular field, there's another right-hand rule. We're going to call it right-hand rule number 2, just so we can keep them straight. This is anytime you have current flowing, you're really using right-hand rule number 2. The first thing you do is you take your thumb. So you're using your thumb, you point it in the direction of the current. So your thumb shows you which way charge is flowing through the wire. And you use your whole hand for this one. You're sort of making a thumbs up, and your fingers on your right hand curl around their thumb. So your fingers curl to show you the direction of the magnetic field. So you want to imagine all 4 of your fingers curling in a circle sort of around your thumb. We'll look at what that looks like with a picture here in a second, but that's how you want to do this. You point your thumb in the direction of the current, your fingers curl for the magnetic field, and that's the whole thing for this one. Okay, here's what that should look like. You want to practice, take your right hand, and in front of your notebook, you want to try this. So try and visualize these images on the right here, where if you have a wire and current is flowing upwards through the wire, you create these circular magnetic fields. So the blue lines show these magnetic field lines that create concentric circles around the wire. Same thing on the left, you see it kind of at an angle. Now those are kind of 3D. That's not how we'll usually draw this. We'll usually draw this like what we see on the left here. So with A, you can see we're going to draw and imagine the wire is going into or out of your page. So you want to imagine a wire actually going straight down through into your notebook page or straight up out of the notebook page in the 3rd dimension. So on the left in A, we draw our 3D vector with a dot, and that represents current flowing out of the page, is how we say that. So imagine a wire coming towards your face, carrying current. That's what you're looking at here. So you want to sketch that, and you want to draw a circle with a dot in the middle to represent that 3D vector, label it with an I to show that that's the current, and then these lines here, you want to take your right hand to point your thumb in the direction of the current, which means for A, you should have essentially a thumbs up on top of your notebook paper. Your thumb should be coming out of the page. Then your fingers curl around to give you these circles that are kind of counterclockwise. These represent the magnetic field, B. So these concentric circles show us that the magnetic field is circular, If the current is flowing out of the page, that field is counterclockwise. Same thing over here, we're going to picture current flowing into the page. So same thing, you have a wire going into your notebook page, like piercing it through. And so I'm going to draw an X to represent the back of an arrow, to represent a vector going into the page. I'm going to call that my current. And I'm going to try and call that my current. And I am going to use my right hand rule then to point my thumb in the direction of the current, which is into the page. So you're going to basically put a thumbs down. Your thumb should be touching the paper of your notebook, and then you turn your fingers to curl, and you should see that they curl clockwise now. So it's the upside down version of what we just looked at. So I have a B field that looks something like this. And that's how you use the second right-hand rule. It just gives you the direction of these circular fields as they loop around a wire. All right, here's where you'll spend the bulk of the time. When things become interesting is when we have two wires. The idea here is each wire creates a circular field, and things will happen because each wire is close to the other one. So just like when we do gravitational work and we talk about a person having a gravitational field because they have mass, there's only a force when there's another mass at play. So until that person is near the Earth, they don't feel a force. So you only feel a force when you're in another field. So you feel a force of gravity because you're in the gravitational field of the Earth. What's going to happen here is this wire I1 will feel a force because it's in the magnetic field of the second wire. And vice versa, I2 will feel a force, the second wire will feel a force because it's in the magnetic field of the first wire. So we know if I have current running through two wires, we're going to draw it this way with current going vertically up. So it's not into the page or out of the page anymore, it's upwards from the bottom of your paper to the top. So imagine little positive charges moving their way from the bottom to the top. Because of that, each wire will create its own magnetic field. All right, this is what it's going to look like for the first wire. You want to practice using your right-hand rule and see if you can visualize this. So take your thumb and point it in the direction of I1. And as you point your thumb upwards, your fingers curl around and they kind of go into the page on the right and out of the page on the left. In other words, the magnetic field looks sort of like this, where it comes around in these circles. This part we don't really draw. Instead, we just draw it with the X's and O's. And what we're showing here is that right here, the field is coming out. And as it loops around and goes back, right here, the field is going in. And makes its way back. So we use these 3D vectors to show, and again, use your right hand to convince yourself that as these loop around, the field comes out on the left and the field goes in on the right. And because I have these big circular fields, at some point the second wire is in the magnetic field created by the first wire. So all we're looking at here so far is the magnetic field created by the first wire with a current I1 flowing through it. So everything is in red. B1 is the magnetic field created by this first wire that has a current going upwards. Because I have current flowing upwards through the second wire, that means I have charges flowing upwards through the second wire. We can imagine a bunch of little charges, a bunch of little positive charges is what we say is current, a bunch of little plus Q's, all flowing upwards through the wire. That's what gives us this current. We said in the previous set of notes, we said that if a moving charge is in a magnetic field, it will feel a magnetic force. That was our QVB force. So there is a magnetic force on each of these charges as they move through the wire, since they're in a magnetic field. So what we need to do at this point is use our other right-hand rule. So you want to look back at right-hand rule number 1, where we talked about the direction of the force on a charge moving through a B field. To do that, we said you're going to take your index finger and point it in the direction of motion. So my index finger goes vertically up. So you're going to take your original right-hand rule where you make the XYZ with your 3 fingers, with your thumb, your pointer, and your middle finger. The current goes up, so your finger points up, so you should be pointing to the top of your page. Then the magnetic field is your middle finger. So the magnetic field here is in. That's what the X means. So since the magnetic field is in, your middle finger should point inwards towards the paper. So you should be making a backwards L on top of your notebook paper at this point. Index finger pointing towards the top, middle finger going into the page, vertically down, straight into your page. And if you do that right, then your thumb should be pointing left. And remember, that shows us the direction of the force. So right-hand rule number 1 tells us all these little positive charges, as they move upwards through a magnetic field pointing into the page, they're going to feel a force to the left. And what really does happen is this wire gets pulled to the left because it's near this other wire, creating its own magnetic field. All right, we're going to try the same thing with number 2. You should pause the video and try this first. So try the same process. You're going to use your right-hand rule, the new one, right-hand rule number 2, to draw the magnetic field due to this second wire. So it would be a good idea to make a new sketch just below. Just draw these 2 wires again because it's going to get a little crowded. Draw the 2 wires again, and now you're going to use this current to use right-hand rule number 2, draw the magnetic field around this wire on the right, then decide which way the force will be on the first wire because of that field. So take a second, pause the video, and try that. All right, hopefully you tried it. Here's what it should look like. As we draw the magnetic field for the second wire, it looks really similar, just shifted to the side, which should make sense. It's all going in the same direction. So you point your thumb in the direction of the current, which is upwards, and your fingers will curl to show you that this magnetic field also comes out and around the front. Comes out and around the front. So over here it's coming out of the page, over here it's going into the page. So a very similar pattern. The only difference is what this looks like to the first wire. Since the first wire is on the left side, when I do my first right-hand rule number 1, to talk about these charges as they move through, I'm again going to have a velocity that's vertically up. So my index finger will again point towards the top of the page, except now the magnetic field from wire 2 at wire 1 is out of the page. So your middle finger flips up, and your middle finger is pointing up out of the page. Your index finger is pointing towards the top of the page. So you are making an L on top of your notebook and giving your partner a bad hand gesture. And your thumb then points to the right, which shows you the force on the first wire is to the right. So what this shows us is that these 2 wires attract. All right, the forces point towards each other. Really, this just comes from Newton's third law. We could say that the force of wire 1 on wire 2 is equal to the negative force of wire 2 on wire 1. All right, we know that's always true. Whenever there's a force of A on B, there's always negative force of B on A. That's what Newton's third law said. This is an action-reaction pair. So they have to be the same size and they're attracted to each other. This will always work, even if both currents were going down. You could try it again. You'll see the same thing. These wires, if there's current going in the same direction, they'll be attracted to each other by this magnetic force. You could also maybe convince yourself, and you're also encouraged to try this by sketching out a new situation with maybe I1 going up and I2 going down. If the currents are in opposite direction, the wires will repel, so they would push away from each other. All right, again, at this point, I would encourage you to go back to that demo video that should be posted with this, where it's very short, just a couple-second video, but it shows you both of those things happening when they run current through two wires close to each other. You don't see this often in real everyday life because we use alternating current, which is something we'll get into later in the course. And also the currents you deal with are usually very small. It takes a large current to really see these forces. All right, last thing you need is the equation for the force on this wire. So again, we said if I have a current going upwards and a magnetic field going into the page, then I'll have a force to the left by the first right-hand rule. We can define the magnetic force. This is going to be a little derivation. It's worth following along in this video, but you don't really even need to copy all of this into your notes. You really just need the equation from the data booklet. But it's worth having a sense of where this comes from, because really it just comes from our first equation, that the force on each individual charge is QVB times the sine of the angle. And that's the angle between the velocity and the B field vector, the magnetic field vector. This would be the charge. If I found every single little charge flowing through the wire, I would find the force on each charge. What I really want is the force throughout the whole length of wire, so I can consider a total charge positive Q. So we think about this, all the little charges added together, we call that big Q. So I'm going to use QVB sine theta again, but I'm going to use the total charge, capital Q. And for V, our one little trick here is we're going to do distance over time. All right, that charge moves, all of that charge moves through a length L in, let's say, a time t. So this is representing V here, the L over t, distance over time. B is still my magnetic field strength. Everything else is the same. And we just do a little rearranging here because we might recognize that Q over T, that's our definition of current. Current is the rate of flow of charge. It's coulombs per second. And so instead of B, Q over TL, we say BIL, or I is the current. And most of our other values are similar to what we had before. So F is the size of the magnetic force on the wire. B is the magnetic field strength. You want to remember that's a new quantity. It's measured in Tesla. I is the current flowing through the wire in amps. L is the length of the wire, and theta is the angle between the current and the magnetic field. So F equals Bill sine theta. That is the second and last equation in your data booklet for 5.4. All right, lastly, to find the direction of the force, just like we practiced, this is just to emphasize that we still use right-hand rule number one. Right-hand rule number one, where you make the XYZ with your middle finger, index finger, and thumb, is always gives you the direction of a force. So the rules are the same, but to maybe help you remember, my index finger still shows me the direction of velocity, the direction that the charge is moving. Since we're dealing with current here, a good way to remember that is that the index finger is for the current, which we use I for current, so index for I. Maybe it can help you remember. But again, same exact rules before. I'm just pointing which way the charge is going. I still use my middle finger for the B field. Your thumb still shows the force. The other nice thing is current. The definition of current is that it's the flow of positive charge. So we don't need to worry about the fourth step where we flip it if it's negative. The current always shows me positive charge, so I can always just go with those three steps. All right, and that's the basics of what you need for calculating a Bill force and talking about a force on a wire. Again, check out some of the MIT video and some of the extra resources on Schoology as you get ready to start doing some practice in this area and getting that right hand rule going.